Okay, so we're looking at an inclined forces review. So this would be forces on an inclined plane, maybe on a cart that's sitting on a ramp, a bicycle, somebody climbing up a hill. Those kind of options or those kind of things would be applicable if we're looking for inclined forces. So going to be able to demonstrate concepts and calculations involving forces on an incline. So this is what we're looking at here. So a little bit of review before we get into the hot and heavy stuff here. We have to know how to do trigonometry. So we have to know how to use sine, cosine, tangent. Okay, we have to know how to use those three trig functions pretty well. So if you don't remember, sine is so, cosine is ka, and tangent is toa. So that's opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. So those are our trig functions that we're going to use. Okay, if we have a triangle over here, these apply to right triangles only. Okay, you have to have these for right triangle trig. Let's say we have a hypotenuse of 5 units for this triangle, and we need to solve it. So we have one angle, we have one value for a side length, and we're missing everything else. So in order for us to find everything else, the angle is pretty easy. We can just figure out what's left from 180 there. But if we want to figure out our trig functions, or we want to figure out the rest of this triangle, we're going to have to use trig functions. So if I wanted to find this side first, so that side is opposite the angle, so I'm going to have to use sine. So we set it up like this. So sine of 35 degrees is equal to opposite over hypotenuse. So that would be x, that side length, or y, I guess, if you want that vertical leg, over 5 units. And then a little bit of quick algebra here. Multiply both sides by 5. And then we'll get our answer. So it'd just be 5 sine 35. And you have to make sure the calculator that you're using is in degrees, not radians for these examples. So x, or that side length, is 2.87 units. Okay, so 2.87 here. If we want to figure out this one next, then that side is adjacent to that angle, so we want to use cosine. So it'd be cosine of 35 degrees is equal to, we can call that x again, since we're just using pretty much straight up right triangle trig here. So cosine 35, that's adjacent over hypotenuse. Okay, that's going to be 5 multiplied again on both sides. So it'd just be 5 cosine 35. And you get 4.095, so 4.1. 4.1 units. So this here is 4.1 units. So you have to be pretty good at right triangle trig if we're doing our inclined plane problem. So if you need a little bit of review on that, check it out. Okay, but now we're moving on. So the next thing we want to consider are free body diagrams. Okay, so free body diagram, you can draw a point. Sometimes people draw a box, but then you're going to draw vectors coming off of that box. So force vectors in whatever direction the forces are working. So then that brings all the concepts of friction and drag and normal force and applied force. Okay, so those kind of forces can be involved. All right, so let's look at something here. Okay, so these are just basic free body diagrams here where we're looking to find a net force. So net force, got to remember what that is. So net force is the sum of all forces in the direction of movement. So if something is moving a certain direction, then there's going to be a net force in that direction. There will be an acceleration in that direction. Okay. If there's no movement or acceleration, so it would be constant. If the speed is constant, then net force is 0. Okay. So you have to consider that as well. If we have a constant speed, there's no acceleration, so net force is 0, and forces are balanced. Okay. So let's look at these 4 scenarios here. What can we say about situation A? Well, if we look at all the forces here, so we have normal force pushing up. Okay, so maybe this is something sitting on a table because we have normal force, which is a surface force, and gravity pulling down 3 newtons. So those are balanced. Okay, and then we look here left and right. our force is going horizontally, friction is 5 newtons, the applied force is 5 newtons. So those are also balanced. So we can say the net force here, so F net, is going to be 0 newtons. Okay, so let's look at B. So we have gravity and normal force. Those are balanced again. And we have one force, that's friction, is pushing to the left or pulling to the left. Okay, so this one is going to have a net force of 5 newtons, and we could just say left, so you could draw an arrow. 5 newtons left, the object's going to be going that way. Okay, which doesn't make sense. Normally friction opposes motion, but in this case that's going to give us a little bit of motion. Okay, so situation C, we have 20 and 20, so net force is 0. And then here we have gravity, 25 newtons pulling down, and air resistance here, 40 newtons pushing up. So that means we have a net force. All right, we got to do with those. We got to subtract those. So it's 15 newtons up. Okay. So maybe in this scenario it could be a skydiver or somebody with a parachute or something like that. They deployed a parachute which caused an upward force, and we got that upward net force. Okay, let's look at a few other examples here. Now we have gravity and tension. So tension is another force that we can look at. So what's the net force here? Okay, so pretty simple again. We got up and down. So 1200 minus 800, we got 400 newtons up. Okay, here we have air resistance, and here we have gravity. So this one we have 600 newtons, 800 newtons. So net force here would be, okay, is 200 newtons down. And then the last one here we're looking at, normal force is 50 newtons, gravity is 50 newtons, so those are balanced. And we have friction to the left again, so we have a net force of 20 newtons left. Okay? So you have to have the direction with your net force here because forces are vectors, and so we have to state which direction we're going in the end. Okay, so these are just basic free body diagrams, kind of looking to see how forces balance out. All right, so now we're going to look at a few examples, and we can kind of change some numbers here. So we have a cyclist going up the hill, and we have a cart that's falling down a hill or down a ramp here. Okay, so we are going to try to figure out what is going to be in these boxes here. So we have, let's do the cyclist first. We have 4 unknowns here, or 2 unknowns, excuse me. So we don't know this box and we don't know this box. Well, let's see if we can figure it out. So this force up that way, that's normally the normal force. Okay, and this one pulling straight down there, that's gravity. And then these dashed lines, well, those are components of gravity. So we call this one the y component of gravity, and this one is the x component of gravity. So that's going horizontally, that's going vertically. Okay, so now the normal force is going to be balanced with that vertical component of gravity. Because if it weren't, then this guy would be either sinking through the ramp or be floating off into space. So we know that this one is going to be 632 newtons because it's balanced with that y component of gravity. Okay. Now we don't really need to use those two. Okay, we just need that one. So now we have left and right movement. Okay, and we have to look here because sometimes we could have somebody that's increasing, we have somebody that's decreasing speed. If it were increasing speed or decreasing speed and we had an unknown right there, then we couldn't really figure it out because we'd have to know how much force is being applied forward, and then we could figure these out. We could take them away or figure out the pieces of it, but if it were increasing, we wouldn't know that. But if not increasing, it is constant. Okay? So since it's constant, that makes this a little bit nicer. So remember what we talked about with the net force stuff here. If there is a constant movement, then net force is going to be 0 newtons. Okay, so we could fill that out up here. So in order for us to get 0 newtons horizontally, we're going to have balanced forces. So for this one, we have 100 newtons of gravity working against us, and then we have 40 newtons of drag. Okay, so that's drag force. So this would be equal to 140 newtons. And we could call that the applied force or something like that. So this biker is applying 140 newtons, which is equaling out the friction and gravitational force going up the hill at a constant rate. Okay, so next example here. So we have to fill out our boxes down here. Okay, so remember this one. We kind of did it over there with the bicyclist, but we worked opposite. So if I have a normal force of 145 newtons, then that is equal to my y component of gravity, so this must be 145 newtons. Okay, now this one might be a little bit more difficult to figure out, but we have this and this, which are essentially legs of a right triangle. So we have the y component, which is 145 newtons, and the x component is 70 newtons. So a little bit of Pythagorean's theorem, we can figure out that piece. So you're going to do square root of 70 squared plus 145 squared, and whatever that gives us, that will be that component. So this component here is 161.01 newtons. Okay, and we just figured that out by using Pythagorean's theorem. A squared plus b squared equals c squared. So that's c squared, you square root, and it'd be a little bit quicker just to use that formula. Okay, so then we know that this thing is increasing going down the hill or down the slant, and we need a net force. So we have a 40 Newton force that's pulling it down. Okay, so maybe this would be tension or something like that. Okay, and then we have this force, which is that piece right there. So this is, again, x component of gravity. This one is just regular gravity. This is y component of gravity. And then this one's going to be drag and normal force. So there's all of our forces that we listed. Okay, technically this and this wouldn't count as a force because they're broken apart from gravity. So we have 4 forces acting here on this little cart. Okay, we got 20 going up the hill, and we got 70 and 40 going down the hill, so that's 110 going down. So we do a little bit of quick math here. 110 newtons minus 20 newtons. So net force is going to be 90 newtons, and we could say it's down the hill. Alright, so that would be how we do some free body diagram analysis. The big thing here is remembering net force, or not net force, excuse me, normal force is equal to the y component of gravity, and then our net force comes from the direction of motion. So we'd have to add everything left and right and figure out what is left over. Okay, so on to the stuff that's a little bit more difficult. So we have a 2 kilogram cart rolling down an incline of 17 degrees, neglect friction and drag impeding the motion of the car. So what are the forces acting on the car? Well, let's draw them. Let's draw a little free body diagram here. So we got gravity, and then we have normal force, and do we have any other ones acting here? It says neglect, friction, and drag. So no, those are the only 2 we have. So, since we just have those 2, we're going to be able to do that. So that is FGY, and then that, FGX. Okay, and then we have that 17-degree angle, so that is important as well. So that's Y, that's gravity, that's X, and that's normal force. Okay, so what are the forces acting on the car? That's gravity and normal force. Are the forces on the car balanced? No, because it's rolling down. Okay, I guess if it doesn't say constant, but we're just going to assume that it has an acceleration here. So find the magnitude of all the forces acting on the car. So we start by writing our net force equation. Alright, so what are the forces acting here? We got gravity and normal force. So gravity's pulling us down. That's going to be the bigger one. Okay, and we don't have anything slowing us down, so really that's it. We just have our net force is going to be equal to the gravitational component. Okay, so how do we get that right there? Well, if you remember that triangle stuff here, so this is a 17-degree angle, which is also in here. Okay, so if this is 17 degrees, we can break these apart and figure out our components. So we need, let's kind of, I'll draw this triangle off to the left here. Okay, we're going down that way. Alright, so that is gravity right there. We got to have that first. So let's figure that out. Force of gravity, that's just going to be mass times gravity. So that would be 2 times 9.81 meters per second squared. So that's going to be 19.62. Oops, that should be newtons. Okay, so we have 19.62 pulling down. We have that angle that goes in there, 17 degrees. And now we're looking for this, okay, because that's what's pulling us down. So really this can be transposed down there, and then we're going to be using the sine of 17. So this, all right, let's write out net force. Fgx is going to be mass times gravity, which is that basic gravity there, times sine theta, because we're looking for that component right there, which is also right there. Okay, so let's just kind of bring those numbers in here. We have 19.62 sine 17 degrees. So put that in your calculator, and we get 5.74. Okay, and that's Newton. So that's the net force. That's also my x component of gravity, because there are no forces acting against us. So it's just 5.74 newtons. Okay, so magnitude of all the forces on the car. We have our net force. Okay, we have gravity, which we wrote down over there, 19.62 newtons. But we only have that one force really. Remember, that is a component of that. So we still need to figure out the normal force. Okay, and how are we going to do that? Well, we haven't used this piece yet, which those pieces are equal. So if we find our y component of gravity, we have the normal force. So let's do that. So Fgy, if this was sine, then this one's going to be cosine. So that's going to be mass times gravity times cosine theta. And we did mass times gravity here already. So it's going to be 19.62 cosine theta, which should be 17. Put that in your calculator, and we get 18.76. So 19.62 times cosine 17 is 18.76, and that is a force, so that's in newtons. So that's our normal force. That's the same thing as that. So F sub n will be 18.76 newtons. Okay, so net force on the car, I kind of jumped ahead. I did that already, because the only force that's pulling us down, the net force, is gravity, the x component. Okay, so we found net force there. And now we need to find the cart's acceleration. Alright, and we have to remember Newton's second law, F equals ma. So that's the same thing as net force. So after we've calculated our net force, we can use mass times acceleration to figure out our net force if we had an acceleration resulting. If we're working backwards trying to find a mass or an acceleration, then we have to have that net force first. So we have that, and we have the mass. So we can use those two numbers to find the acceleration. So the mass is 2 kilograms. Okay, and now we're just looking for the acceleration. So we'll have to divide both sides by 2. And we get an acceleration of 2.87. And that's in meters per second squared. Okay, so these problems can be pretty large just because we have so many things that we have to write out. But it's nice that we don't have any friction because this is the only thing pulling us down the slope. Okay, when there's friction involved, then we'll have to find the force of friction that's resisting our motion. But for this one, we don't have that. Okay? So the next example is we have a cyclist. Okay, so 70 kilogram cyclist pedaling uphill, increasing speed at a rate of 1.8 meters per second, so that's acceleration. The cyclist is experiencing a 40 Newton drag and no friction impeding the motion of the bicycle on the track. Find all unknowns. So we're looking for all of these. Okay, so we have 70.0 kilograms for the mass. We have an acceleration of 1.8 meters per second squared. Net force, we're going to have to figure that out. And speed, we want that to be either increasing or decreasing. So we know that this person is increasing speed because it says so in the problem. So we need to find the net force. Okay, so we can find the net force pretty easy for the problem because we're given the mass of the person and we're given a rate. So really, right away, if we wanted to figure out the net force, we know that net force equals mass times acceleration. So we have F net equals 70 kilograms times the acceleration, which is 1.8 meters per second squared. Okay, so you just take 70 times 1.8, and we'll have the net force, which is 126 newtons. Okay, so there's 126 Newton force that is left over going up the ramp. Now, that's a pretty simple problem. I want to break everything down to figure out what the applied force is here, how fast the person is pedaling. So let's get rid of this, and let's see if we can figure out the applied force. All right, so let's draw our vectors again. So we got gravity pulling down. We have drag working against us, so force of drag or force of air, and then we have normal force, that's the perpendicular to the surface. Okay, and then we also have an applied force because he's accelerating, or this person is accelerating up the ramp, okay, at 1.8 meters per second. So we know that there's going to have to be some kind of an applied force that is beating drag. It's going fast or pulling more than drag because he's increasing. Okay, so let's list everything here. We also need to draw this little guy. So that's FGY, the y component. Remember, we're going to have to use cosine to get that, and we have FGX. We have to use sine to get that one. So let's start by writing out some things that we know. We know we can figure out force of gravity. So that is 70 kilograms times 9.81 meters per second squared. All right, that's a pretty quick one to figure out. So 70 times 9.8 is 686, nice number. And that's newtons. Okay, now this is going to start breaking apart here. We know we have the force of drag. We could write that down. Okay, that's 40 newtons. And now we're going to have to use this to figure out the other pieces. Okay, so if gravity, that's 686. Okay, so it might help to draw a triangle. So this is FGY, this is FGX. That's 686 newtons. And our angle here is 13 degrees. That might help you if you draw that off to the side to kind of figure out FGX, FGY. Okay, I'm going to write them somewhat like a formula over here. So if we want that x component, that's going to be mg sine theta. And if we want the y component, that's going to be mg cosine theta. Okay, So we have mass times gravity already, so that's 686. So 686 times So 686 times sine 13, we'll get that, and 686 cosine 13, we'll get that. Okay? So 686 sine 13 is 154.32 newtons, and I'm not really paying attention to significant figures here. I'm just kind of throwing it in there. I'd rather spend more time getting the problem done than worrying about sig figs for this one. Okay, and then we have 686 cosine 13, and that gives me 668.42 newtons. Okay, and we probably could have started with a net force equation, which might have made more sense, but that's okay. Let's do that here, way at the top. Okay, normally you can start with the net force equation and then start breaking stuff apart. I just wanted to really get rolling there, apparently. So the forces we have going left and right, we have that applied force, okay? And then we have drag and the x component of gravity pulling us down. So force of drag, and that would be the FGX. Okay, and that is why I started breaking things down. Okay, and looking back again, we really didn't need that, but it's good practice. Okay, so let's rewrite our net force equation down here. All right, and remember we found that net force earlier. We just had F equals 70 times 1.8 meters per second squared, 70 kilograms. All right, and we had that as a 126, so let's write that back over here, and we'll use that down here. So let's just write values in here that we have, and then we'll be able to solve for that applied force. So I have 126 newtons, that's my net force. My applied force, I don't know, that's what we're looking for, minus drag, which the problem tells us is 40 newtons, and minus FGX, which is 154.32 newtons. Okay, which that's what we found. So then we can add 40 to both sides and add 154.32 to both sides. So that would just add to the 126. Okay, so we end up getting 320.32. Alright, so that person is applying 320.32 newtons in order to have a net force of 126 newtons. Okay, so hopefully this information helps you with basic inclined plane problems. I'll continue and make another video in regards to inclined planes with more things working on them, and we have more friction or we have tension and stuff involved. So be looking for that video if you want more of this stuff. Thank you.